The third-order intercept point is a critical metric for understanding an RF amplifier's nonlinear behavior. And in this video we'll measure it on the Tekbox TBMDA3B high-gain, high-power wideband amplifier. But there's a twist. The first measurement goes very wrong and falls below the expected datasheet value. Let's find out why. Before we troubleshoot, here's the essential theory. In an ideal world, an amplifier would output a perfectly scaled version of its input. Real amplifiers don't. Even with a single tone, the output includes harmonics, which is integer multiples of the input frequency. To show this, the Tekbox TBMDA3B is connected to a Rigol RSA5065N spectrum analyzer through a 30 dB attenuator. With a maximum output power of roughly 8 watts, the attenuator is essential to avoid damaging the analyzer. A 20 MHz tone at -5 dBm is applied, and the resulting harmonics up to the third harmonic at 60 MHz are visible. Harmonics alone are usually easy to filter. The situation changes once the input contains more than one frequency component, which is typical for real-world signals. With two tones, F1 and F2, the amplifier generates additional intermodulation products through nonlinear mixing. These products are classified by their order. Of particular interest are the third-order products at 2F1-F2 and 2F2-F1, which appear close to the desired tones and cannot be filtered easily. To demonstrate this, the test setup is slightly modified. A resistive splitter is used to feed 20 MHz and 21 MHz tones into the amplifier, each at -5 dBm. The output spectrum clearly shows the third-order intermodulation products near the fundamentals. Third-order intermodulation products have a particularly important characteristic. As the input power increases, they grow at roughly 3 times the rate of the fundamentals. A 1 dB increase in the desired tones produces about a 3 dB increase in the third-order products. If this trend continued indefinitely, the third-order products would eventually reach or even exceed the level of the fundamentals. In reality, the amplifier enters compression long before that happens. Compression occurs once the output no longer increases with the expected gain, and a common reference point for this behavior is the 1 dB compression point, where the amplifier's gain has dropped by 1 dB from its small signal value. To visualize IP3, the linear portions of both curves, fundamental output versus input power, and third-order product output versus input power, is taken and extrapolated beyond the compression region. These extended lines intersect at a purely theoretical point known as the third-order intercept point, often abbreviated as TOI or IP3. IP3 can be measured by applying a two-tone signal to the amplifier input and inserting the measured output powers of the fundamentals and the third-order intermodulation products into a simple equation. The result can be referenced either to the output, referred to as OIP3, or to the input, referred to as IIP3. The two values differ only by the amplifier's gain. With the theory in place, let's measure. The device under test is driven with two tones at 20 and 21 MHz, each set to -5 dBm, supposedly below the 1 dB compression point specified by the manufacturer. Instead of calculating the TOI manually, the Rigol RSA5065N's advanced measurement kit is used. It automatically tracks the fundamental tones and the third-order intermodulation products and computes the TOI. The output tones and the third-order products are clearly visible. The resulting TOI is calculated to be 41.5 dBm. But wait, that's far below the value Tekbox specifies. Tekbox lists a third-order intercept point of 44 dBm. Although their specification is given at 100 MHz with a 2 MHz tone spacing, the result from this setup should be very close. So either Tekbox overstated the TOI or something in the test setup is wrong. When a measurement differs from expectations, the safest assumption is that the measurement is at fault. And spoiler, that assumption turns out to be correct. The first potential source of error is excessive input power at the spectrum analyzer. High levels can create third-order products in the analyzer itself. To check this, an additional 6 dB attenuator is inserted. If analyzer overload were the issue, the measured TOI should increase, but it doesn't. This is expected because the analyzer was already set to use a sufficient amount of additional internal attenuation. The second potential source of error is insufficient isolation between the two generators. If one tone leaks into the other generator, it can generate intermodulation products at the source. To test this, two 10 dB attenuators are inserted, one at each generator output, raising port-to-port isolation by 20 dB. The generator outputs are increased by 10 dB each to maintain the desired -5 dBm output power from the splitter. After repeating the measurement, nothing changes. This is also expected. The combined tones themselves already have a TOI of around 27 dBm. Through a perfectly linear amplifier with 40 dB gain, this would scale to about 67 dBm, far above the amplifier's expected TOI and therefore irrelevant. Nonetheless, the attenuators remain in place as good practice. The real issue lies elsewhere. The input drive level. The -5 dBm per tone used so far appears to be below the 1 dB compression point, but compression starts before the amplifier reaches that specific point. And importantly, the 1 dB compression point is defined for a single tone. To put it simply, the 1 dB compression point indicates the highest total output power at which the amplifier still behaves mostly linearly. For a two-tone signal, even assuming an ideal amplifier with no harmonics or nonlinear distortion, the power of each tone must be reduced by 3 dB. Backing off the -3 dBm datasheet input power by 3 dB alone would require an input level no higher than -6 dBm. The -5 dBm used earlier exceeds this theoretical limit and drives the amplifier too close to compression, causing severe distortion that corrupts the IP3 measurement. To ensure linear operation and provide sufficient headroom for all third-order products, the input power is now reduced significantly to -10 dBm per tone. With the drive levels now correctly set and all other error sources accounted for, the TOI is measured again and now aligns almost perfectly with the datasheet specification.